Let omega be a unit circle with diameter AB and center O. Let C and D be on omega and lie on the same side of AB such that angle CAB is equal to 50 degrees and angle DBA is equal to 70 degrees. Suppose that AD intersects BC at point E. Let the perpendicular from O to CD intersect the perpendicular from E to AB at point F. Find the length OF. So, in order to solve this problem, we have the angle COD as follows because we can end up connecting the lines CO and OD. And this is equal to 50 degrees as given. This is also 50 degrees, and therefore this is 80 degrees by the sum of the angles in a triangle. Similarly, this is 70 degrees as given, so this is also 70 degrees, and this angle here is equal to 40 degrees. And therefore, since angle AOC plus COD plus DOB is equal to 180 degrees, we have that angle COD is 60 degrees. Now, since CO is equal to OD and CF is equal to FD, since F lies on the perpendicular bisector of CD, this is because FO is perpendicular to CD, we see that we need to just calculate the angle CFD, at which point we will be done because angle OCF and angle FDO are equal, and then we can just use this angle, the sine law. So let's go ahead and put our efforts to calculating the angle CFD. So in order to calculate the angle CFD, things look a bit complicated, but we might be able to make things a bit simpler. So let's see if we can identify what the point F is. So, and after a bit of looking, we conjecture that the length FC and FD also seem to be equal to the length FE. In particular, we conjectured that F is the circumcenter of triangle CDE. So how do we prove this conjecture? Well, we already know that F lies on the one perpendicular bisector. Now we just need to show that it lies on a line passing through the orthocenter. And now we have that F lies on another line containing E, and therefore we need to prove that the perpendicular from E to AB contains the circumcenter of CED. How can we do this? Well, recall in a cyclic quadrilateral that triangle CED and AEB are oppositely similar, which means that when we have an altitude here, then an altitude in AEB is just an isogonal of the altitude in CED because of the cyclic quadrilateral. And because of the cyclic quadrilateral, this means, and because the circumcenter and orthocenter are isogonal in a triangle, that means that this line passes through the circumcenter, and hence this claim is true. Now that we know that F is a circumcenter of CDE, we can use the inscribed angle theorem to finish. So we have angle CFD. By the inscribed angle theorem, this is equal to 360 degrees minus 2 times angle CED, because CED is isosceles. And now we just need to calculate the angle CED. So in order to do this, we can look at the triangle CED itself. Then this angle here is 70 degrees, so that means that this angle here is 20 degrees, as is this angle here because of the cyclic quadrilateral. And similarly, this angle here is 50 degrees, making this one 40, and as is this one. Therefore, because 20 plus 40 plus 120 is 180 degrees, angle CED is 120 degrees. So this is 360 degrees minus 2 times 120, which is 120 degrees. So now we have that these angles here, we calculated them all. This one is 60 degrees, and this one is 120 degrees. And this implies that angle COD plus angle CFD is 180 degrees. So angle FCO is equal to angle FDO, which sum to 180 degrees, which means that they are both 90 degrees. So that's 90 degrees. And since FO bisects COD, because FO is a perpendicular bisector, this is 30 degrees. So therefore, we have that triangle COF is a 30, 60, 90 triangle. So this is what COF looks like. So here is O, C, and F. It's a 30, 60, 90 triangle. Furthermore, CO has length 1 as given by the problem statement here, the word unit here. Therefore, this length here is 1 over root 3 because of the properties of a 30, 60, 90 triangle, and therefore FO is equal to 2 over square root 3. And after clearing denominators, this is 2 times the square root of 3 over 3. Thank you so much for watching this video. Please subscribe if you'd like to see